Hello and welcome to a new lecture in a course on linear algebra. In this video, I plan to cover the definitions of kernel and image of a linear transformation and to give some examples and properties of these. So we're gonna start off by defining what a kernel is and giving some examples. But before that, let me just remind you real quick of the definition of a linear transformation. So the setup is that we have two vector spaces, v1 and v2 are vector spaces. A linear transformation T from v1 to v2 is a map that satisfies the following. It satisfies that T of v1 plus r v2 is equal to T of v1 plus r times T of v2. So this should happen for every v1 and v2 in the domain, and for every, so these are small v's, and for every real number r. So this is what a linear transformation is. Now we're going to define something called a kernel. So the kernel of a linear transformation, so let's say we started with a linear transformation T from a vector space V to a vector space W, and the kernel of it is going to be defined the set of all vectors that whose image is 0, right? So it's the set of all V's in the domain such that they map to 0. Right, so this set is called the kernel, right? So one thing that we're gonna prove about this kernel is that it's a subspace of the domain. But for now, what we know is that this is a subset of the domain V, right? Because we're taking all the vectors V in V that gets mapped to 0. So it's important to note that this is a subset of the domain. So this is a subset of V. Alright, so let's take an example here. So consider the linear transformation from R3 to R2, right? That takes the tuple of size 3. So it takes a vector x, y, z. It takes it to x plus y, y plus z. Now, proving that this is a linear transformation is an easy thing to do, and I'm gonna leave it to you as an exercise to check this. But as you see, if you plug such a thing inside in place of this, where v1 is also a tuple of size 3 and v2 is also a tuple of size 3 and r is a real number, you see that it's going to be clear that from the element-wise defined addition and scalar multiplication that this is actually a linear transformation. Now let's see, what is the kernel of this linear transformation? Well, the kernel, it's the set of all vectors that gets mapped to 0. But what are vectors in the domain? Well, vectors in the domain are of this form, right? So we're asking what vectors of the domain, right? What vectors of the domain gets mapped to 0, meaning that this should be 0, 0. So this is the question. So what is xyz? What is the vector xyz if the output is 0? Well, this is what this equality tells us, right? It tells us that it's the set of all vectors in R3 that have the property that x plus y is 0 and y plus z is 0, and we're seeing this from comparing these two as such. So the kernel in this case, it's clear from the definition, it's the set of all vectors that satisfy this property. So let's take an example of a vector that is in the kernel. So for example, you can take the vector 1, -1, and 1, for example. So this is a vector in R cubed, so it's in the domain, but I'm claiming that it's in the kernel. Well, why is it in the kernel? Well, it's in the kernel because if you take T of this vector, what do you get? Well, you get you get this thing, right? You get this output. which is the first component plus the second component, which is 0, and then you take the second component plus the third component, which is also 0, and thus this is the 0 of R2, and thus this vector is in the kernel, which implies that 1, -1, 1 is in the kernel of T, right? So so there, like, for simplicity, or sometimes you might it might be better to rewrite this in a simpler form as such. So you see that since x is equal to -y from this first equation, you see that x is equal to -y, and from the second one you have z is equal to -y. So if you just replace x here by -y and z by -y, you see that the vectors in the kernel take the form -y, y, excuse me, as y runs over R, right? So you can write the kernel in this compact form. So this is what the kernel is, and this is an example of a kernel of a linear transformation. So the next thing we want to show, now we want to show a property of the kernel, which is that it's a subspace of the domain. So let's say we have a vector space, we have two vector spaces V and W, and we have a linear transformation between this. So this is a linear transformation. Then we claim, so I remind you, this is the kernel, it's the set of all vectors in V that gets mapped to 0. Then our claim is that the kernel is actually a subspace of V, right? So I remind you, a subspace is just a vector space that is contained that is a subset of a bigger vector space. However, we claim that, however, we've shown in a previous video that it's easier to verify some other criterion. Let me just remind you here of the definition of subspaces. So let V be a vector space, then if S is a subset of V, S is called a subspace of V if and only if first we require that S not to be empty. And I told you that some people require the 0, or like they mentioned the equivalent requirement, which is that the 0 should be in S, but these are the same. The second property that we need is closure under addition and scalar multiplication. So we require that S is closed under scalar multiplication and addition. And thus this proves, and this is what it takes for a subset of V to be a subspace of V. Alright, so we're gonna prove now, since the kernel we know it's a subset of V, okay, we want to prove that it's a subspace. So first we need to prove that it's not empty, and then we're gonna prove that it's closed under addition and scalar multiplication. So this is what we're required to prove. We're required to prove that first it's not empty, and we're gonna show this by showing that 0 is in the kernel. Right? If we show 0 is in the kernel, then it's not empty, clearly. And second, we need to show closure under addition, meaning if we start with any two vectors in that set, the sum of these should also be in that set. This is what it means for closure under addition. And we also require closure under scalar multiplication, meaning if we start with V, we want to prove that so here we're talking about C in real numbers. We want to prove that C dot V is also in the kernel. Alright, so let us see how to prove this. This should be easy. However, there are some tricks that I hope that you'll keep track of when you see. So let's start by the first one. Why is 0? So why is 0? Let me just prove it over here. So why is 0 in the kernel? What does it take for a vector to be in the kernel? It should be that its image under T is 0. So let's take T of 0, and if we can prove that this is equal to 0, then this 0 is in the kernel. So T of 0 is equal to what? Well, we know that this is something that I've shown you in the previous video. We know that T of 0 is equal to 0 because because we know that T of RV is equal to RT of V. And this happens for any V and any real number R. So if we take R equals 0 and any V in V, right? If we take these in this property, because T is a linear transformation, it satisfies this, then we have T of 0 dot V is equal to 0 dot T of V, and this right hand side is 0 and this input is 0 by a property that we proved in a previous video, and thus T of 0 is actually equal to 0. So this is the first thing that we just shown, which is that the kernel is not empty. So we just proved property 1 that we wanted. Now the second thing we want to show is closure under addition. So we want to start with any two vectors in the kernel and want to show that the sum is there. So what does it take for the sum to be there? Well, it takes that T of that thing, we require T of that thing to be equal to 0. But what is T of that thing? Well, since T is a linear transformation, T of u plus V is T of u plus T of V, right? And this is equal to, well, since u is in the kernel, then T of u is 0. But since V is also in the kernel, then also T of V is 0. And thus this is equal to 0 plus 0, which is just equal to 0. And this proves that u plus V is in the kernel of T. So the third thing we want to show is closure under scalar multiplication. So if we start with V in the kernel, then T of V is equal to 0. And we want to take any real number C and want to show that C dot V is also in the kernel. But why is that the case? Well, because T of CV, C dot V, is equal to C times T of V, because T is a linear transformation, and thus this is equal to C dot the 0 vector. But any number times the 0 vector is the 0 vector, and thus this implies that CV is actually in the kernel of T. So this proves that the kernel is a subspace of the domain, is a subspace of V. And this happens for any linear transformation T. This is very important to keep in mind. Anyways, and here's a cleaner proof for you if you want to look at this. If you want to look at this in a cleaner solution. So here's a cleaner solution for you. So the next thing we want to define is the image. So what is the image? Well, you take a linear transformation, like you take a linear transformation from V to W, and V and W are vector spaces. The image, it's the set of all vectors that are hit by T. So let us draw a picture here, because we're introducing new concepts. So we have this T. It goes from the vector space V to the vector space omega, right? Or W. So the kernel, it's the set of all vectors in. So there is inside V, there is something called the kernel of T, right? And this kernel has the property that all these vectors gets mapped to 0. So this is what the kernel is. Now, what is the image? The image, it's the set of all vectors that are hit by T. So what does that mean? Well, it means it's something in W. So the image is something in W that takes V, like that it's something in W that T, that when we apply T to every vector in V, we get that thing. Right? So let me just use mathematical notation here and show you what I mean. So the image of a linear transformation T, it's T of V for every V in V, right? So you might have vectors here going here, vectors here going there, and you collect all these in the image, you collect all these vectors in omega, and you call them the image of T, right? Because we're taking all the images of all the vectors in the domain, right? So here's an example for you just to refine this. Here's an example for you. So if we take the same example that we took before when we studied what the kernel is, and we want to find what the image is for this, right? So you see the codomain is R2, right? And thus, if you look at this, you see that this is a subset of omega, right? This is a subset of W, excuse me. So this image, so the image of T, what we know is that the image of T is actually a subset of R2. So in other words, since for any vector in R cubed we have this image, the image of T, it's the set of all vectors in R2 where the first component is x plus y and the second component is y plus z as x, y, z ranges over R. So let me just restate this for you, because the image of T, right, the image of T, it's actually the set of all T of x, y, z such that x, y, z is actually in the domain, and the domain here is R cubed. What is T of x, y, z? Well, T of x, y, z is the vector x plus y, y plus z, and we have the same thing over here. So you don't stop here, you do something more. You do something more to understand what this set is, right? So it turns out that this set is in fact equal to R2. And how do you show that? You want to show that every vector in the image gets hit by the linear transformation. So every vector in R2, there's some vector here that goes to it, right? And to see this, okay, so let me show you here why the image is R2. If you start, if AB is in R2, if you start with a vector in R2, what vector x, y, z can you choose in R3 such that T of that vector is equal to AB? Here's what you can do. Well, you want T of something, 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 such that when you take T of it, you have AB. So this is what you want. And the reason we're showing this is that we're claiming that the image is actually equal to R2, right? Because we know that this is a subset of this. We know that the image is a subset of this. And now we're taking an element here and we're trying to show that it is here. How do you show that an element here is here? Well, an element is in the image if there is a V, in the domain such that it's equal to T of V, right? So this is what we're trying to show here. So what's the so what kind of vector can we choose in R3 in the domain so that the image is AB? You see, like, we can just take like the vector A, 0, B, right? And then the image is gonna be the first plus the second in the first component. So it's gonna be A plus 0, which is A, and then the second component is gonna be the second component plus the third component, which is 0 plus B, which is B. And thus every element in R2 is actually hit by T, and thus the image is the whole of R2, right? So this is what we got. So this is the concept of the image, and this is an example of it. So the next thing we're going to show is that we're going to show that the image is actually a subspace of the codomain. We're going to show that the image is a subspace of the codomains. So let us do that. So I remind you, the image, it's the set of all T of V as V ranges over V. And let's say T is a linear transformation from V to W. And then the image of T, of a linear transformation T, is a subset of omega. And to show that the image is a subspace of omega, what we need to show is that we need to show that it's not empty, and we need to show that it's closed under addition and scalar multiplication. So here's what we want to show. We want to show that 0 is in the image, and thus it's not empty. And then we need to show closure under addition and scalar multiplication. So let us do that. So why is 0 in the image of every linear transformation? Again, to show an element is in the image, you need to find an element in the codomain which gets mapped to that element by T. Okay? So here's a small picture for you, just for you to recall how to show an element is in the image. So if this is the image, right, to show that this, let's call it, I don't know, let's call it small omega, for example. To show that omega is in the image, what you need to do is that you need to find an element here such that the image of that, if you take t, let's say this is v, you need to show that t of v is equal to omega. If you show that t of v is equal to omega, then you see omega has the form t of some vector, and thus since it has the form t of some vector, it's in the image, right? So this is how you show that a vector is in the image, right? So why is 0 in the image? You need to find a vector which gets mapped to 0 by t, right? If you found that, then 0 is in the image. So you notice here that we've seen before like we've seen previously in this lecture, that t of 0 is actually equal to 0. And thus, since we find a vector in the vector space V whose image is 0, is the 0 vector, then 0 of omega, so this is the 0 of W, right? So this 0 is actually in the image of t, right? So this is the first thing which shows that the set is not empty. So the next thing is closure under addition. So why is that the case? Why is it the case if u and v are in the image, then their sum is in the image? So let us prove this. So to prove 2, let u and v be in the image of t, and we want to show that their sum is in the image. So u is in the image, then since u is in the image, then we have there is some u prime, where since t is actually a linear transformation from v to w, since u is in the image, this means that there is some u prime in v such that t of u prime is equal to u. So this is the definition of being in the image. It means that there's a vector that gets mapped to it. And since v is in the image, then there exists a v prime in the image, in v, excuse me, such that t of v prime is equal to v. So this is what we know. And now we want to show that the sum is in the image. But what is the sum? The sum u plus v, from here, we see that it is equal to t of u prime plus t of v prime. But wait a sec, t is actually a linear transformation, which means we can get the sum inside, and it's going to be t of u prime plus v prime, right? But this is a vector in v, right? Since this is a vector in v and it gets mapped to u plus v, this implies that u plus v is actually in the image. So this is the trick, like you use what you know, and you use the fact that t is linear, and you get the thing that you want. So the third thing we want to show is that if v is in the image, we want to show closure under scalar multiplication. If v is in the image, we want to show that if we take any real number c and multiply that by v, then cv is actually in the image. So let us see this. So we're gonna start with v in the vector v, vector space v, and a real number c, right? A real number c, and we want to check that. We want to start with v in the image, right, of t, and we want to check that c dot v is in the image, right? So this is what we want to show. We want to show closure under scalar multiplication. So why is that the case? Well, we know since v is in the image, then there exists a v prime in v such that t of v prime is equal to v. So this is by the definition of the image. Now let us look at cv, right? C dot v. We want to show that c dot v is in the image. Thus, we want to show that there is a vector in v which gets mapped to cv by t. But cv is actually equal to c dot t of v prime. And this is equal, since t is linear, we can get the constant inside, and this is gonna be T of CV prime. But CV prime is in V because V is a vector space, and thus we just shown that there's a vector in V that gets mapped to CV, which implies that CV is actually in the image of T. And this shows closure under scalar multiplication. This proves that the image is a subspace of the codomain as desired. And here's a cleaner proof for you if you wanna look at a cleaner proof. Just leave it for you here.